Deep inside the moon, there's a layer of rock that shouldn't exist at all, at least not according to anything scientists thought they understood before 2024. It's warm, it's genuinely, measurably, partially melted. And by every model scientists had before 2024, that layer should have gone completely cold and solid over 1 billion years ago. Nobody was looking for it at all. When the gravity numbers first came back, the researchers analyzing them assumed they'd made an error. They hadn't made any mistake at all, and that's only the first shocking piece of a real ongoing wave of lunar research that's quietly rewriting what NASA thought it knew about our closest neighbor in space, right as astronauts prepare to head back there for real. For decades, the moon got taught the same way in every classroom: a dead rock. A frozen, geologically finished ball of gray dust and craters that stopped doing anything interesting billions of years ago, hardly worth another close look. New instruments, more advanced than anything previously pointed at our closest neighbor, have started proving that description wrong in ways that are actively reshaping NASA's Artemis program and its plans for the next decade of lunar exploration. Start with something simple: temperature, because it explains a lot of what follows. Stand on the lunar surface during the day, and it sits near 120 degrees Celsius, hot enough to boil water instantly. Wait for sunset, and within hours, that same spot drops to roughly minus 130 degrees. That's a swing of about 250 degrees between day and night, repeating month after month for billions of years. Do that to any solid material long enough, and it cracks, weakens along its natural fault lines, and eventually shifts. NASA's Lunar Reconnaissance Orbiter, mapping the moon in detail since 2009, has spotted thousands of small cliffs called lobate scarps scattered across the surface, essentially fault lines where the crust has buckled under pressure. What makes plenty of these scarps genuinely notable to planetary scientists is that they look geologically young. On a world that's 4.5 billion years old, something that formed within the last 50 million years counts as almost brand new, and a meaningful number of these scarps appear to fall into exactly that category. T. Hatt tells researchers the moon's crust isn't just carrying old scars. It's still under active stress. There's direct evidence of that stress sitting in data that's been waiting since the 1960s. Seismometers left behind by Apollo astronauts recorded real moonquakes, some reaching a magnitude of 5, strong enough to shift loose surface material and trigger small landslides in areas orbital images show are already unstable. When researchers reran that decades-old Apollo data through modern computing tools, several of the fault lines responsible for those quakes appeared to have been active surprisingly recently in geological terms. You can actually see evidence of this in orbital photographs, certain slopes showing fresh, sharp-edged material that has clearly slid downhill recently, standing out against older weathered ground nearby. What you're looking at is loose surface dust called regolith sliding, in response to moonquakes, extreme temperature swings, or the constant hammering of tiny space debris that slowly loosens the upper layer of dust and rock over millions of years, since the moon has no atmosphere to slow incoming particles down at all. This matters directly for NASA's Artemis program, since figuring out which patches of ground are genuinely stable, rather than just appearing stable in old photographs while hiding active fault lines underneath, is a direct astronaut safety. Question: 1. Engineers are actively factoring into where future landing and habitat sites actually get chosen. If watching real, current NASA and international research quietly overturn the moon is a dead rock idea most of us grew up with, is exactly the kind of story you come here for, go ahead and subscribe, because that's exactly the territory this channel covers. Now to the deeper mystery, because what's happening below ground on the moon is arguably a bigger deal than anything happening on its surface. In 2024, researchers at NASA Goddard and the University of Arizona, led by Sander Goossens, published a study in the journal AGU Advances analyzing new gravity data from NASA's GRAIL mission alongside the Lunar Reconnaissance Orbiter. GRAIL flew 2 small spacecraft in close formation around the moon back in 2012, and as they passed over regions with slightly different gravitational pull, the 2 spacecraft drifted almost imperceptibly closer together or farther apart. By measuring those tiny shifts with extraordinary precision, scientists mapped the moon's gravity field in unprecedented detail and used it to infer what's happening deep inside the moon, somewhere no camera will ever reach. Their models simply couldn't reproduce the real gravity and tidal measurements without adding in a softer, partially molten layer sitting between the solid mantle above and the metallic core below. Without that layer, the numbers refuse to work. The research suggests that layer likely consists of a mineral called ilmenite, rich in titanium and iron oxide, and researchers believe this mineral might be exactly what's trapping enough heat to keep the layer molten. Here's where it gets genuinely interesting for anyone thinking about long-term lunar bases. Titanium is one of the most valuable materials in modern engineering, prized for its combination of strength, low weight, and resistance to heat and corrosion, showing up in aircraft parts, spacecraft frames, and high-performance machinery. If the moon really does contain a titanium-rich molten layer, that's a potential resource sitting there for any future permanent human presence, and pulling raw material directly from the moon would be dramatically cheaper than hauling the same material out of Earth's gravity well, still the single most expensive part of any space mission. There's a genuinely elegant piece of detective work behind how researchers connected this molten layer to something visible in older data. Years earlier, Grail had detected an odd polygonal pattern of gravity anomalies surrounding the dark volcanic plains on the moon's near side, dense rock formations nobody could fully explain at the time. Researchers eventually realized these patterns matched computer simulations of what should happen if a dense ilmenite layer, formed early in the moon's history near the surface, gradually sank down through the mantle over billions of years under its own weight. Rather than sinking as one smooth mass, the simulations showed the layer fracturing into flat sheets that cascaded downward in a series of waterfall-like structures, eventually freezing in place as they cooled and leaving behind exactly the polygonal gravity signature Grail had already recorded. Some of that sinking ilmenite is thought to have partially melted along the way and later resurfaced as titanium-rich lava, the same material Apollo astronauts collected samples of decades ago without fully understanding where it had originally come from. But here's the mystery this discovery created that scientists still can't fully answer. How is that layer still partially molten at all? The moon is 4.5 billion years old and should have lost the vast majority of its internal heat by now. Its core is far smaller relative to its size than Earth's, meaning it generates far less internal heat to begin with. Researchers suspect the titanium and iron oxides in that ilmenite layer might be unusually good at trapping and holding onto heat, but exactly how it has stayed warm this long remains an open question that follow-up studies are actively working to answer. For more than 50 years, scientists have suspected the moon might hide underground lava tubes, hollow tunnels carved out by ancient lava flows, during a period when the moon was volcanically active. The logic came from studying similar features on Earth, in places like Hawaii and Iceland, where a lava flow's outer layer cools and hardens while molten rock keeps flowing through the middle, eventually draining away and leaving a hollow tube behind. On the moon, where gravity is only 1/6 of Earth's and ancient eruptions were far larger, the same basic process would have produced tubes on a completely different scale. In 2024, researchers at the University of Trento in Italy confirmed exactly this using radar data reflected back from underground structures beneath the Mare Tranquillitatis region, the same area where Apollo 11 touched down in 1969. What they found was a cave at least 100 meters deep and potentially hundreds of meters wide, likely just one of many similar structures scattered across the lunar surface, all remnants of the same ancient volcanic system. This matters enormously for future human exploration because a natural underground cave provides something no surface structure can easily match: automatic protection from radiation. The lunar surface sits fully exposed to solar radiation, cosmic rays, and constant micrometeorite impacts, meaning any surface habitat needs heavy, expensive shielding just to keep occupants safe. A cave cut into solid rock already provides that shielding for free. NASA's own measurements show that areas just below the lunar surface hold a remarkably steady temperature, around 17 degrees Celsius, regardless of the extremes happening above. On a world where surface temperatures swing 250 degrees between day and night, a natural shelter sitting at a stable 17 degrees is an extraordinary find, and engineers are now seriously discussing building humanity's first permanent lunar base inside one of these lava tubes rather than out on the exposed surface. Even the safest cave still needs water, and that's exactly where the story turns to the lunar poles and to some of the strangest real estate anywhere in the solar system. The moon barely tilts on its axis, roughly 1 degree compared to Earth's 23, which means the sun never climbs high above the horizon near the poles, and inside the deepest polar craters, sunlight never reaches the floor at all. Shackleton. Crater at the lunar South Pole stretches more than 20 kilometers wide and plunges over 4 kilometers deep, its floor sitting at a permanent temperature around minus 200 degrees Celsius, unlit for billions of years. In cold that extreme and that ancient, any water that ever arrived there has nowhere to go. It simply stays frozen in place. Back in 2009, NASA deliberately slammed a spent rocket stage into one of these permanently shadowed craters and flew a second spacecraft through the resulting debris cloud, producing the first direct confirmation of water ice inside lunar soil. Since then, orbital data and refined modeling have painted an increasingly detailed picture of ice steadily accumulating inside these permanently shadowed polar craters over well over 1 billion years, layer upon layer, largely undisturbed since long before complex life existed on Earth. Current estimates suggest the total amount frozen inside these craters could run into the hundreds of millions of tons. That ice exists as microscopic crystals mixed directly into lunar soil, rather than sitting in an accessible lake, meaning extraction would require drilling and heating the soil just enough to release water vapor, then capturing that vapor before it escapes into vacuum. The engineering challenge is genuinely difficult, but the payoff would be enormous because water can be split into hydrogen and oxygen using solar power, and hydrogen and oxygen happen to be rocket fuel. A lunar base sitting on a water supply like that could manufacture its own propellant on the surface, turning the lunar South Pole into a refueling station for missions heading deeper into the solar system, since launching off the moon takes a fraction of the energy required to launch off Earth. This is precisely why NASA and other agencies keep describing lunar water ice as a genuine strategic resource rather than just a scientific curiosity. Every kilogram of propellant a spacecraft doesn't need to haul up out of Earth's gravity, well, is a kilogram of extra cargo, extra crew supplies, or extra scientific equipment that mission planners get to send instead. A functioning lunar fuel depot would fundamentally change the math behind any mission heading toward Mars, or deeper into the solar system, letting spacecraft launch from Earth relatively light, refuel at the moon, and continue outward with far more capability than launching. Everything from Earth's surface in one go could ever allow. NASA has identified specific ridgelines near the South Pole, nicknamed peaks of eternal light, that sit in near constant sunlight thanks to that same minimal axial tilt. And some of these ridges sit close enough to the permanently shadowed craters that running power cables between the two is genuinely feasible. Picture a solar farm on a sunlit ridge, an ice mining operation working in the frozen darkness just below it, and a crew habitat tucked inside a nearby lava tube for radiation shielding, all working as one connected system. That's the actual working blueprint multiple space agencies are building toward. This is where the Artemis program itself enters the picture directly, because none of this research is happening in a vacuum separate from actual mission planning. Artemis II already sent astronauts around the far side of the moon, making them the first humans in over 50 years, to see that hidden hemisphere in person, and setting a new distance record for crewed spaceflight along the way. Artemis III is targeting a landing near the South Pole, aiming for one of several candidate landing zones clustered within a few degrees of the pole, each one chosen by balancing enough sunlight for solar power against proximity to those shadowed ice deposits. That's not a coincidental overlap. NASA is deliberately steering its first crewed lunar landing since Apollo directly toward the exact region where this molten interior, these ancient lava tubes, and this billion-year-old ice have all turned up in the same stretch of research. China's Chang'e 7 mission is separately heading toward that same lunar South Pole, chasing the exact same ice deposits, and when multiple national space programs converge on the same small patch of a world within the same handful of years, that tells you everything about how valuable that ice, and everything sitting near it, has become. It's worth understanding just how much site selection for a crewed landing actually depends on details like these. Choosing where to put astronauts down on an entirely alien surface with no atmosphere, no rescue infrastructure, and a communications delay measured in seconds rather than minutes is one of the most consequential decisions in the entire Artemis program. Engineers have to weigh dozens of overlapping factors simultaneously: terrain slope and roughness, how much direct sunlight a site receives across a full lunar day for solar power, how close it sits to scientifically valuable ice deposits, and how stable the ground actually is once you account for exactly the kind of active fault lines and moonquake activity discussed earlier in this video. Every one of the 13 candidate landing zones NASA has shortlisted near the South Pole represents a different set of trade-offs across those same variables, and the research covered here is precisely the kind of data feeding directly into which of those 13 sites eventually gets chosen for astronauts to actually set foot on. It's worth pausing on just how directly these discoveries feed into real engineering decisions happening right now. Mission planners choosing a landing site have to weigh solar power availability, terrain stability, radiation exposure, and proximity to water ice all at once. And every one of the discoveries covered here speaks directly to one of those four factors. A region riddled with young, active fault lines is a landing hazard. A nearby lava tube is a radiation shelter. A titanium-rich layer deep underground is a long-term resource question for later missions. Permanently shadowed ice is the difference between hauling every drop of water from Earth and manufacturing it on site. None of this is separate from the human spaceflight program. It's actively steering it. Put it all together, and the moon that Artemis astronauts are about to walk on looks almost nothing like the one described in decades-old textbooks. It holds a partially molten, titanium-rich layer nobody predicted, somehow still warm after 4.5 billion years. Its surface keeps cracking and sliding under brutal temperature swings and genuine moonquakes strong enough to trigger landslides. Underneath it all sit lava tubes wide enough to shelter entire future colonies, discovered directly beneath the very ground Apollo 11 first touched in 1969. And at its poles, inside craters that haven't seen sunlight since before complex life existed on Earth. Out. None of this sat in the textbooks a generation ago. Some of it wasn't even known 5 years ago. Every claim here traces back to actual missions, actual instruments, and peer-reviewed data collected within the last 2 years. And the gap between what we assumed about the moon and what we now know has never closed this fast. Nor is it likely to slow down anytime soon, given how many active research programs are still chasing these exact questions right now. Think about what that actually means for the next few years. Artemis astronauts are scheduled to walk within a few degrees of that ice-packed South Pole, standing above a molten titanium layer. Nobody expected, beside lava tubes that could shelter the first permanent lunar residence in history. If you made it this far, you now know more about what's actually happening beneath the surface of the moon than most people will ever bother to learn, and every one of those hidden details is quietly shaping exactly where humanity chooses to land next in a decision process unfolding right now, not in some distant hypothetical future. If deep dives into real current space research like this are what you come here for, make sure you're subscribed. Because this story is moving fast enough that the next surprise could land within months, not years. And if any single discovery here changed how you picture the moon, let me know in the comments, and I'll see you in the next one.